Yesterday we started doing analysis on noise margin. We didn't complete it, but we derived expressions for the VIL and VIH. Okay, what is VIL and VIH? We'll look at it now. V out versus V in. This is my transfer characteristic. V in, V out. Right? So we said that the point at which the slope, right, becomes -1 is a point of interest, because to the left of it on the lower side the gain is less than 1, which means any noise will get killed, will get attenuated, and the output will be robust and stable at that particular value, right? So therefore the point where the gain becomes -1 is of importance. G equal to -1, right? And what is G? dV0 by dV in, the gain, right? So we needed to identify these points. So the point where this is VIL, VIH. Corresponding y axis value is VOH for VIL, because it's an inverter, and VOL, right? So we wanted to find these points in a short channel transistor. Because it has channel length modulation, all that, the expression is quite complex. Therefore we made an approximation and said that we will find the point when V in equal to V out equal to Vm, the trip point, right? V in, V out equal to V in equal to line, and this point is Vm comma Vm. Then we said that we will take the slope out here and just extrapolate with that slope, right, and see where it intersects my thing. So the first point is VOH is actually nearly VDD and VOL is nearly ground. This is true whether it's a real transistor or the ideal case or the real case, it doesn't matter, right? So VOH, if you are going to approximate as VDD, is not a big problem. So we can take the intersection, and this point we said we would call as VIL. Similarly, this particular point we would call as VIH. Of course, there will be slight error, but it's a very reasonable error. Within 5% or so, we get the answer, right? This is the basic idea, because the expressions are complex. Okay, you can always try to derive it, but it's just going to get very cumbersome. Okay, so then we said that you can calculate the gain at, so you calculate the gain at V in equal to V out equal to Vm, right? How do you do this? You have to basically do dV out by dV in, right, at V in equal to V out equal to Vm. Of course, both NMOS and PMOS are going to be assumed to be in velocity saturation region in this particular, at this particular point, Vm. We already did this calculation earlier, right? Using this, we were able to calculate the levels VIL and VIH. So what was VIL? It was Vm, right? What was that plus term? Can you remind me? Vm plus Vm by G, is it? VIL. VDD minus Vm by G. And VIH minus Vm by G, is it? Yeah, makes sense, because G is a negative gain. Minus minus will become plus, so VIH is to the right of Vm. and VIL will be to the left of thing. So this is the expression that we got. Now still this doesn't tell us anything about the noise margin. That's what our discussion started with. So let's now see what these values mean. What is VIL? It's the threshold voltage, right? Not to be confused with transistor threshold. It's that particular threshold voltage below which everything will be treated as a logic 0. VIH is the threshold voltage above which everything will be treated as a logic 1. Okay, that's the most important thing. So now let's assume in the limiting case that I am applying VIL here. What will be the output of this inverter? No. Go back to this curve. If the input is VIL, then the corresponding output is VOH. By definition, because that's the y-axis value, right? Therefore, this has to be VOH, right? Now, I want this output to be recognized as a logic high. What is the condition on the second inverter? This is I1, I2. What is the condition on the second inverter for this VOH to be recognized as a logic high? Correct. VOH should be greater than VIH. Which means that if there is a noise pulse up to this magnitude, the difference of VOH and VIH, it should be fine. My VOH is here, right? My VOH is somewhere here. My VIH is somewhere here, right? This is VOH, this is VIH. VOH is above VIH. As long as that's done, taken care of, it's a logic high, no problem. That means I have this much room for noise to actually, cause this voltage to come down. That much I can tolerate. Naturally, this is called the noise margin on the high side. So noise margin high is NMH is VOH minus VIH. Okay. Now, if this is VIH, what will the output of the inverter be? I1. VOL. What is the condition for VOL to be recognized as a logic low for on inverter 2? VOL should be less than VIL. Correct? So, this is my VIL and somewhere here is my VOL. Therefore, on the lower side, I can tolerate a positive noise pulse. As long as it is below VIL, I am fine. So this much is my noise margin on the low side. So NML is VIL minus VOL. Okay. So now can you substitute these values? Of course, VOH very close to VDD. Correct? So we can make the substitution that VOH is nearly VDD. So this is in black, right? So this is VDD minus VIH. What is that value? VM minus VM by G. Right? Similarly, what is noise margin low? VOL is what? Yeah? 0. So this is just VIL. So this is what we derived again, VM plus VDD minus VM by G. VM plus VDD minus VM by G. Now, sanity check. Ideal inverter. What is G? Yeah? Infinity. What should the noise margin be? On the high side, VDD minus VM, right? Because for the ideal inverter, the VTC is going to look like this, right? It starts abruptly at VM, it will fall. This is VDD, VM. The noise margin on the high side is going to be VDD minus VM. On the low side, it's just going to be VM, as long as I have that much room. And that's exactly what we get when we substitute G equal to infinity. So the expressions we have got are in alignment with our intuition as well. Okay? Any questions here? Yeah. Yeah, because they are actually very, very close to VDD and ground. I mean, you can calculate the exact value, but they'll be really, really, really close. That is true. The approximation method does that. But even otherwise, VOH and VOL will be very close. You do a simulation and see, for example, find out where the slope goes to -1 and see what VIL and VOL are, VOH are. VOH will be very, very close to VDD, right? For reasonably high VDD, this will be true. Okay. Yeah. So now let me see how far this approximation that we have made, how far can I take it? Can I apply the same logic to a long channel device? Think about the approximation that we did. Tell me if I can make this approximation for a long channel device. How would this approximation look for a long channel device? First of all, how will the VTC of this long channel device look like? Rather, what will be the slope at the trip point? Huh? What is the slope G at the trip point? More than, no. I need a number. Huh? So we derived this yesterday. Suppose it was a long channel device, right? At V in equal to VM equal to V out, IDSN is what? Half of Kn prime Wn by L into Vm minus Vtn the whole squared. IDSP is what? Half of Kp prime Wp by L. Both are in saturation. Vm minus Vdd minus Vtn by Tp whole square. Do any of these currents depend on V out? No. So what will be the slope? There is no lambda. That's the whole point, right? So we derived an expression for the gain. right? If you remember yesterday, and we said it is 1 by 2 lambda n, assuming that lambda n equal to minus lambda p. If now lambda n is 0, what happens to the gain? Goes to minus infinity, right? Basically, or it goes to plus infinity. Why are you saying minus infinity? There's a minus, yeah, right. Anyway, it basically becomes a vertical line at that point. This does not mean that the voltage transfer characteristics of a long channel device inverter is an ideal case. It doesn't mean that long channel VTC is like this. That's not true. What actually happens is, this guy is like this, it comes, now at this V in equal to V out, here it will be a straight vertical line. Your slope will be infinity. Okay, then it's again go out like that. So the conclusion is, if I do this same analysis and approximation for a long channel device, I will get this blue curve, and my VIH and VIL will both collapse to Vm. If I make the approximation, right, then here VIL equal to VIH equal to Vm. Clearly this is not true, right? So the approximation that we did works only for a short channel device when there is non-zero channel length modulation. That's the limitation of the approximation that we have made earlier. So this guy here works only when CLM is greater than 0. This is the limitation that you should understand. When CLM is there, it's a reasonable approximation because you get a slope at that point, you extrapolate and it works reasonably well. But you cannot do this for a long channel device. Okay. So now question is, how do I evaluate these noise margins for a long channel inverter? Luckily, it turns out the expressions for current are themselves not so complex as it is for a short channel device, and therefore we can do it from first principles. Okay.